On November 19th, 2025, at NASA's Goddard Space Flight Center in Maryland, a group of the agency's most senior science leadership sat down in front of live cameras and did something NASA rarely does for a single object. They held an entire press event dedicated to releasing a flood of new imagery, gathered not from one telescope, but from 12 separate NASA missions, all trained on the same target, an interstellar comet called 3I Atlas, only the third confirmed visitor our solar system has ever received from beyond our own sun's neighborhood. What came out of that room, and what continued to arrive in the months afterward, genuinely reshaped how much we understand about this object, and about the deep, ancient history it's been carrying through the galaxy for longer than our own solar system has existed. This is the real story of what those images actually showed, why NASA assembled such an enormous coordinated fleet to capture them, and what scientists eventually found hiding inside the light itself. Comet 3I Atlas was first spotted on July 1st, 2025, by the NASA-funded ATLAS survey, the Asteroid Terrestrial Impact Last Alert System, based in Rio Hurtado, Chile, part of the Planetary Defense Network that continuously watches the sky for anything dangerous. Almost immediately, astronomers realized this object was moving on a hyperbolic trajectory, meaning it was traveling too fast for the sun's gravity to ever capture it into orbit. It wasn't a local resident of our solar system. It was a genuine visitor, passing through from interstellar space on a one-way trip that would eventually carry it back out again forever. Digging through archival images from other telescopes around the world, including the Zwicky Transient Facility at Palomar Observatory in California, astronomers traced observations of the object back even further to mid-June 2025, nearly 3 weeks before its official discovery. It became only the third confirmed interstellar object in recorded history, following Oumuamua in 2017 and Borisov in 2019. And unlike Oumuamua, which showed almost no visible activity, 3I Atlas behaved unmistakably like a comet, actively venting gas and dust as sunlight warmed its surface, giving astronomers a real, bright, trackable target rather than a fading blur. To understand why NASA cared enough about this one object to coordinate such an enormous response, it helps to know just how rare genuine interstellar visitors actually are. For the entire history of astronomy before 2017, every comet and asteroid ever studied up close came from our own solar system, built from the same original disk of gas and dust that formed the Sun, Earth, and everything else here. Oumuamua broke that streak in 2017, tumbling through so quickly and showing so little activity that telescopes barely got a good look before it faded from view entirely. Borisov, in 2019, behaved more like a conventional comet, giving scientists their first real chemical read on interstellar material. 3I Atlas turned out to be the best opportunity yet. Bright, active, and slow-moving enough, relative to the scale of the solar system, that dozens of instruments across multiple space agencies had real time to study it in depth before it disappeared again for good. Because genuine interstellar visitors are so rare, NASA didn't just point one telescope at it and call it done. Over the following months, the agency coordinated what it later described as an unprecedented solar system-wide observation campaign, turning spacecraft and instruments positioned all across the solar system toward this single object as it made its journey through. The Hubble Space Telescope captured what NASA called the sharpest ever picture of the comet on July 21st, 2025, when it was still 207 million miles from Earth, revealing a teardrop-shaped cocoon of dust streaming off its solid, icy nucleus, with the background stars streaking in the image because Hubble had to track the comet's fast motion across the sky, rather than simply pointing at a fixed target. From that observation and later follow-ups through August 20th, Hubble helped narrow down the size of the comet's icy core, eventually placing its diameter somewhere between about 1,444 feet and 5 miles across. But Hubble was only one piece of an enormous coordinated effort. NASA's SPHEREx observatory, designed to study the broader history of the universe and the ices scattered throughout it, trained its instruments on 3I Atlas from August 7th through August 15th, when the comet was still roughly 290 million miles from the Sun, capturing detailed information about its coma, the hazy envelope of gas and dust surrounding its nucleus that functions almost like a temporary, borrowed atmosphere. As the comet swung closer to Mars in late September and early October, an entirely different set of NASA assets got their chance. 3 separate spacecraft already stationed at Mars turned their instruments toward the passing comet. The high-resolution imaging science experiment, known as HiRISE, aboard the Mars Reconnaissance Orbiter, captured an image on October 2nd, 2025, when the comet was about 19 million miles from the spacecraft, the closest imagery of 3I Atlas ever obtained by any instrument. Just days earlier, on September 28th, NASA's MAVEN spacecraft, which has been studying Mars's atmosphere since 2014, used its ultraviolet imaging spectrograph to capture a striking composite, showing the hydrogen atoms surrounding the comet, glowing in ultraviolet light, invisible to human eyes. Then, on September 16th, NASA's Lucy spacecraft, originally launched to study the Trojan asteroid sharing Jupiter's orbit, added its own contribution, stacking a series of images as the comet zoomed toward Mars, capturing 3I Atlas as a faint circled point of light against the starfield. Around the same period, NASA's sun-watching missions joined in as well. The Punch satellites, the Solar and Heliospheric Observatory, and the Stereo A spacecraft all captured their own sequences, with Stereo A's visible light imager producing a colorized, stacked composite from September 11th through the 25th, showing the comet traveling at roughly 130,000 miles per hour as it crossed the inner solar system. Even NASA's Perseverance rover, sitting on the actual surface of Mars, got a chance to look upward and contribute its own observation of the passing visitor. Taken all together, this meant a single interstellar object was simultaneously being observed from Earth orbit, from deep space, from the vicinity of the Sun, and from the surface of another planet entirely. A genuinely unprecedented spread of vantage points for any comet, interstellar or otherwise, in the history of astronomy. Each of these missions brought something genuinely different to the table, rather than simply duplicating each other's work. Hubble and Webb, positioned to study extremely faint and distant objects with exquisite precision, provided the sharpest possible images and the most detailed chemical spectra. SPHEREx, built to survey enormous swaths of sky at once, offered a broader look at the comet's overall composition. The Mars-orbiting spacecraft, by sheer accident of timing, ended up providing the closest physical vantage point of the entire campaign, simply because 3I Atlas happened to sweep past Mars during its journey. And the sun-watching spacecraft, normally focused entirely on solar activity, offered a completely different visual perspective, tracking the comet's motion against the backdrop of the inner solar system rather than the distant stars. No single mission could have produced the complete picture on its own. It took all 12, each doing what it was originally built for, pointed at the same target by coincidence and coordination in equal measure. Here's the part of the story that explains why all of this imagery arrived in one giant release on November 19th, rather than trickling out as each mission captured it. A lapse in federal government funding had put work at NASA and other federal agencies on hold for an extended stretch, delaying the public release of images that had, in some cases, already been sitting on hard drives for well over a month. When the shutdown ended and the agency resumed normal operations, NASA's science leadership, Associate Administrator Amit Kshatriya, Science Mission Directorate Associate Administrator Nikki Fox, Acting Astrophysics Division Director Sean Donegal-Goldman, and Tom Statler, the agency's lead scientist for solar system small bodies, held that live event specifically to walk the public through everything that had been quietly collected during the gap, all at once. That's the real reason. November 19th became such a dense, sudden flood of imagery. Not a single new discovery breaking in that instant, but months of careful, patient, multi-mission observation finally reaching daylight together after being held up by circumstances that had nothing to do with the comet itself. NASA continued observing 3I Atlas well beyond that release, too. In mid-January 2026, the Transiting Exoplanet Survey Satellite, TESS, a spacecraft normally used to hunt for planets orbiting other stars by watching for the tiny dips in starlight as a planet passes in front of its host star, conducted a special dedicated observation run specifically to study 3I Atlas's activity and rotation, adding yet another instrument's perspective to the growing archive of data on this single object. By the time the comet passed the orbit of Jupiter in the spring of 2026, it had been observed, tracked, and imaged by more individual NASA missions than perhaps any other small solar system body in recent memory. A genuinely unprecedented level of coordinated attention for a single passing visitor. So why did NASA go to such extraordinary lengths for one comet? Because every one of those images and instrument readings gave scientists a chance to study something they'd almost never get access to again. Raw physical material that formed around a completely different star long before our own sun ever existed. And when researchers finally sat down to analyze the full spread of data gathered across that entire campaign, what they found went far beyond pretty pictures. The James Webb Space Telescope's contribution turned out to be the most scientifically significant piece of the entire effort. On August 6, 2025, Webb's near-infrared spectrograph observed 3I Atlas directly, revealing a coma dominated overwhelmingly by carbon dioxide, alongside water vapor, carbon monoxide, a sulfur-bearing molecule called OCS, water ice, and dust. The ratio of carbon dioxide to water vapor came out at roughly 6 to 1, among the highest such ratios ever measured in any comet anywhere, and a striking departure from the water-dominated comets typical of our own solar system. Separately, researchers also measured an unusually high proportion of methane relative to water in the comet's plume, roughly 11 times higher than anything cataloged from comets native to our own solar system. Taken together, these anomalies were the first solid hint that 3I Atlas's raw ice inventory simply didn't match anything humanity had previously cataloged. Then, on June 22nd, 2026, NASA released a paper published in the journal Nature, led by astrochemist Martin Cordner at NASA's Goddard Space Flight Center, using additional supporting measurements from the Atacama Large Millimeter Submillimeter Array in Chile that pushed the story even further. According to that analysis, 3I Atlas may be somewhere between 10 and 12 billion years old, potentially older than our own sun and solar system, which only formed about 5 billion years ago. In Cordner's own words, released in NASA's public statement, this was a unique opportunity to study an ancient object from a distant part of the galaxy, one that likely predates our sun and solar system entirely, giving scientists both a direct window into that distant era and a lesson in just how unusual our own solar system's chemistry might actually be. That age estimate rests on two independent chemical clues, both extracted from the same body of spectroscopic data gathered across that enormous imaging campaign. The first came from measuring deuterium, a heavier isotope of hydrogen, inside the comet's water ice, which showed roughly 30 times more deuterium relative to normal hydrogen than comets native to our own solar system typically display. Jacqueline McCleary, an assistant professor of physics at Northeastern University, described this so-called heavy water signature as a direct marker of an intensely cold formation environment, one where regular hydrogen atoms had far more time and opportunity to be gradually replaced by their heavier deuterium cousins. This kind of isotope measurement is one of the most reliable tools astronomers have for reading a comet's formation history, precisely because deuterium enrichment builds up slowly and predictably under specific temperature conditions, then stays locked into ice essentially unchanged for billions of years, undisturbed unless something actively melts or reprocesses it. The second clue came from carbon. Researchers detected unusually scarce traces of carbon-13, a heavier isotope of ordinary carbon, in the comet's material. Because heavier elements like carbon build up gradually across successive generations of stars living and dying throughout galactic history, with each generation of dying stars seeding the surrounding galaxy with slightly more of these heavier elements, a comet with especially scarce heavy element enrichment likely formed before the galaxy had gone through very many of those stellar life cycles at all, pointing, once again, toward extreme age. What makes this two-part case particularly compelling is that the deuterium measurement and the carbon-13 measurement are essentially independent lines of evidence, arrived at through entirely different physical processes, and yet both point toward the same staggering conclusion about the comet's age and origin. When two unrelated chemical clocks agree that closely, scientists treat the resulting picture as far more reliable than either measurement would be on its own. McCleary offered an analogy for just how foreign this chemistry looks compared to anything in our own solar system. Studying 3I Atlas, she said, felt something like sequencing the genes of a rose and unexpectedly finding the genetic signature of a fern instead, recognizably related at the most basic level, but separated by so much time and divergence that the result looks like it belongs to an entirely different branch of the tree. In her own words, this object clearly did not originate within our own cosmic gene pool. That age estimate connects this one small, icy visitor to one of the biggest unresolved questions in modern astrophysics: what conditions actually looked like during cosmic noon, the period roughly 2 to 3 billion years after the Big Bang, considered the peak era of star formation in the universe's entire history. Astronomers have spent years using Webb to photograph extremely distant galaxies from that same ancient period, but all of that research relies on light that has traveled here across billions of light years. Researchers can measure brightness, color, and broad chemical signatures from a distance, but they can never physically sample the material itself. 3I or Atlas offered something categorically different: actual physical matter from that same ancient era, close enough for direct spectroscopic sampling, rather than just photons arriving from unimaginably far away. McCleary put it plainly: investigating 3I Atlas's chemistry is a genuine way to start understanding how solar systems assembled themselves during this pivotal, still poorly understood chapter of the universe's history. That age estimate connects this one small, icy visitor to one of the biggest unresolved questions in modern astrophysics: what conditions actually looked like during cosmic noon, the period roughly 2 to 3 billion years after the Big Bang, considered the peak era of star formation in the universe's entire history. Astronomers have spent years using Webb to photograph extremely distant galaxies from that same ancient period, but all of that research relies on light that has traveled here across billions of light years. Researchers can measure brightness, color, and broad chemical signatures from a distance, but they can never physically sample the material itself. 3I Atlas offered something categorically different: actual physical matter from that same ancient era, close enough for direct spectroscopic sampling, rather than just photons arriving from unimaginably far away. McCleary put it plainly: Investigating 3I atlases chemistry is a genuine way to start understanding how solar systems assembled themselves during this pivotal, still poorly understood chapter of the universe's history. Nearly everything astronomers otherwise know about cosmic noon comes from distant, hands-off observation. This campaign flipped that arrangement, delivering ancient matter directly into our own solar system for the first time. There's also a deeper implication buried in the chemistry, one that reaches into one of the oldest questions humans ask about the cosmos. How common are the specific conditions that allow life to exist at all? As far as we currently know, Earth remains the only confirmed place in the universe where life has ever existed, built on a foundation of liquid water and elements like carbon and oxygen. If 3I Atlas genuinely formed in a metal-poor environment during cosmic noon, lacking many of those same building blocks in meaningful abundance, that's a real physical data point, suggesting the raw ingredients for life may simply not have been widely available across large parts of the galaxy during much of its early history. In McCleary's words, if there isn't much of the necessary chemical building material available, the odds of finding much life in that particular environment, at that particular moment in cosmic history, go down substantially. That's not a claim that life is impossible elsewhere. It's a genuinely useful, sobering data point about how special or common Earth-specific chemical recipe for biology might actually be, gathered from real physical evidence rather than pure speculation. It's worth remembering, too, that all of this unfolded alongside a very public debate about what 3I Atlas might actually be. Not long after its discovery, prominent Harvard astrophysicist Avi Loeb raised the possibility, in public interviews and published commentary, that the object's size, trajectory, and behavior might indicate something other than a natural origin, potentially even an engineered probe. Loeb pointed to the comet's non-gravitational acceleration, its unusual size estimates, and the timing of its closest approach to the Sun, which happened to occur while the object was hidden behind the Sun from Earth's perspective, as reasons worth taking the possibility seriously rather than dismissing it outright. He even created what he calls the Loeb scale, a 0 to 10 rating system for how likely any interstellar object is to be artificial, placing 3I Atlas at a 4 during the peak of the debate. Genuinely uncertain, not dismissed, but far from confirmed either. That speculation received serious attention and equally serious scrutiny from the broader scientific community. Richard Moisel, head of planetary defense at the European Space Agency, stated plainly that there had been no signs pointing to a non-natural origin in any of the available observations. Multiple independent observing teams, drawing on exactly the kind of enormous 12-mission dataset NASA had assembled, ultimately converged on the same conclusion. The object's outgassing, its chemical signatures, and its overall behavior are entirely consistent with a natural comet, and a dedicated search turned up no evidence of any artificial radio signal whatsoever. What's genuinely remarkable, looking back at the full campaign now, is that the real answer turned out to be almost stranger than the alien probe theory. Not a spacecraft, but a comet potentially old enough to have formed while the universe itself was still in its early adolescence, drifting quietly through this galaxy for roughly 2/3 of the entire history of everything, before wandering close enough to our particular star at exactly the moment humanity happened to have 12 separate spacecraft ready and positioned to notice it. 3I Atlas is now on its way back out of the solar system permanently, following its closest approach to the Sun on October 29th, 2025, and its closest approach to Earth on December 19th, 2025, at a safe distance of about 1. 8 astronomical units, or roughly 270 million kilometers, never posing any threat to Earth at any point in its passage. But the enormous body of imagery and spectroscopy gathered during that unprecedented 12-mission observation campaign isn't going anywhere. Researchers are continuing to comb through the archive, looking for additional chemical signatures and isotope ratios that might further pin down exactly which corner of the galaxy and which specific era this particular ancient traveler actually formed in. There's a genuine lesson in how this story unfolded that's worth sitting with. NASA didn't need to invent anything to make 3I Atlas feel extraordinary. It coordinated 12 separate spacecraft and telescopes, spanning from Earth orbit to the surface of Mars, to build the most thoroughly documented portrait of an interstellar visitor humanity has ever assembled. And when a government shutdown delayed the public release of that imagery, the agency simply held a single comprehensive event once things resumed, walking the public through everything at once, rather than trickling out speculation in the gap. And when scientists finally sat down with the full data set, the chemistry told a story more remarkable than any invented headline could have offered. A comet potentially older than our own sun, carrying frozen evidence of a version of the galaxy that existed billions of years before Earth ever formed. Think about the sheer scale of coordination this actually required. Each of the 12 missions involved has its own dedicated team of engineers and scientists, its own operational schedule, its own primary mission objectives that had nothing to do with comets in the first place. Lucy is meant to study asteroids near Jupiter. MAVEN is meant to study the Martian atmosphere. PUNCH is meant to study the sun's outer corona, getting all of them to briefly redirect their attention toward the same fast-moving temporary visitor on overlapping but not identical schedules across a span of several months represents a genuinely impressive feat of institutional coordination, the kind of thing that rarely gets appreciated by the public because the end result looks, superficially, like just another set of pretty space photos rather than the product of dozens of separate teams quietly rearranging their schedules to seize a narrow, unrepeatable opportunity. It's also worth remembering just how temporary this particular opportunity really was. 3I Atlas entered our solar system, became briefly observable, and is now on its way back out permanently, following its closest approach to the Sun on October 29, 2025, and its closest approach to Earth on December 19, 2025, at a safe distance of about 8 astronomical units, or roughly 270 million kilometers, never posing any threat to Earth at any point in its passage. Every image, every spectrum, every isotope measurement gathered during that campaign represents data that can never be collected again from this particular object. There will be no second flyby, no follow-up mission sent to catch up with it, no opportunity to double-check a measurement that seems unclear years from now. Whatever NASA's fleet managed to capture during those few months in late 2025 and early 2026 is, permanently, all the direct physical data humanity will ever have about this specific 11 billion-year-old traveler. That reality is part of why the 12 mission coordination mattered so much in the first place. With the target this fleeting, redundancy isn't wasteful, it's essential. If one instrument's data turned out to be ambiguous or incomplete, having 11 other independent observations to cross-reference against dramatically increases confidence in the final conclusions. That's exactly what happened with the age estimate. The deuterium measurement alone might have been treated cautiously as a single, isolated anomaly, but combined with the independently gathered carbon-13 measurement, and cross-checked against the broader chemical picture assembled from Hubble, Webb, SPHEREx, and the rest of the fleet, researchers could state their conclusion with real published confidence rather than tentative speculation. 3IR Atlas is now on its way back out of the solar system permanently, but the enormous body of imagery and spectroscopy gathered during that unprecedented 12-mission observation campaign isn't going anywhere. Researchers are continuing to comb through the archive, looking for additional chemical signatures and isotope ratios that might further pin down exactly which corner of the galaxy and which specific era this particular ancient traveler actually formed in. Every future interstellar visitor humanity detects, and astronomers expect them to become far more common as newer, wider field survey telescopes like the Vera C. Rubin Observatory come fully online, will be measured, in part, against the detailed template this campaign has now established. If you want to check any of this yourself, everything here traces back to NASA's own 3I Atlas science pages and multimedia archive, the agency's November 19th, 2025 press briefing at Goddard Space Flight Center, the June 22nd, 2026 Nature paper led by Martin Cordner at NASA Goddard, and the on-record interview with Northeastern University astrophysicist Jacqueline McCleary. All public, all citable, all gathered by real missions with real names attached, rather than a single dramatic transmission arriving out of nowhere. Subscribe if you want more of these stories told the way they actually happened. Because when you actually follow the real timeline, 12 NASA missions quietly working together to photograph one ancient wanderer turns out to be a far bigger story than any fake countdown clock could ever capture.